Hi everyone. Welcome to another practice problem walkthrough video from physacademy.com. In this video, we'll work through a very complete problem. We'll sketch a PV diagram of a cycle, then calculate each state's pressure, volume, and temperature. And we go even further by calculating the exchanged work and heat and change in the thermal energy of each process. Let's read the problem statement and analyze it together. 3 moles of an ideal gas are subjected to the following processes. In the first process, the volume is tripled in an isobaric process. Then, in the second process, it undergoes an isothermal process to a pressure of 9 kilopascals. In the third process, the volume is then halved in another isobaric process. And in the last process, finally, it returns to the original state in an isochoric process. In Part A, draw a PV diagram of the cycle. Label each state with a letter A, B, C, and D. For the transitions, number them with the corresponding number and arrows showing the direction of the process. In Part B, if the isothermal process occurs at a temperature of 900 kelvins, what is each state's pressure, temperature, and volume? In Part C, for each of the processes. First, find the work done on the gas. Second, find the heat in and out of the gas and the change in thermal energy. In Part D, find the total work, exchanged heat, and the change in thermal energy. Let's start from Part A. Starting with the PV diagram, we keep volume along the horizontal axis and pressure along the vertical axis. Then, we mark the initial state and call the volume of this point V0 and the pressure P0. Then, we draw a curved line that passes through this point. This is the temperature line of this point, and we can call this line T0 temperature line. Alright, in the first process, the volume is tripled in an isobaric process. Let's call the ending state B, and its volume is 3V0, but its pressure is the same since we have an isobaric process between A and B. Let's sketch the temperature line of B. In the second process, the gas undergoes an isothermal process to a pressure of 9 kilopascals. Through an isothermal process, the temperature remains the same, so we stick to the same temperature line and go backward toward smaller volumes. But to find out how far back we go, we can check the third and fourth processes. If the volume in the third process is halved and no change in volume in the fourth process occurs, then it means the volume of point C needs to be 2V0. In the third process, the gas, through an isobaric process, goes from 2V0 to the original volume. In the last step, the gas goes through an isochoric process and goes back to its original state or A. Here, we have the axes labeled, and the temperature lines are clear and labeled. For states A, B, C, and D are marked, and the processes are marked with arrows showing their direction. Volumes and the pressure are labeled. We know the pressure of C and D are 9 kilopascals and the relative volume of states B, C, and D with respect to A. In Part B, we will calculate each state's pressure, volume, and temperature. We know the pressure at points C and D are 9 kilopascals. Pascal is a standard SI unit, so we can leave these values as they are, and there is no need to convert them. The temperature of points B and C are also given. Their temperature is equal to 900 kelvins. Again, Kelvin is the standard unit of temperature, so we don't need to convert it. Now, let's mark the values we know are going to be equal or have some clear connection. We know the pressure of A and B are equal. We also know that the volume of B is 3 times and C 2 times larger than A, while the volume of A and D are equal. As you see, point C is the only state we have 2 of the 3 variables, so let's start calculating the volume of this point. Using PV equals nRT, we calculate the volume to be 2.492 meter cubes. Going back to the table, we know the volume of D and A are half of this value. So the volume of A and D are 1.247 meter cubes, and the volume of point B is half larger than C. Again, the same as the previous state, we have 2 out of the 3 variables of states B and C. We could use PV equals nRT again, but also we can use proportionalities. Let's practice this method instead. As shown, using a closed system states equation, we find the pressure of point B to be 6 kilopascals. Updating our table, now we know the pressure for points A and B. Again, using the proportionality relation, we can calculate the temperature of A as 300 and D as 450 kelvins for points A and D. Updating our table, we have all of the values. In part C, we'll calculate the exchanged work, heat, and the change in the thermal energy of the system through each of the processes. Let's list everything in two identical tables, as shown. We'll use the left one to list the equations we need to use and the right table for listing the actual numerical values. We already know that in an isothermal process, the thermal energy doesn't change, so for the B to C process, delta E is 0. We also know that from D to A, the work exchange in an isochoric process is 0. Let's focus on the A to B process. In an isobaric process, the exchanged work is equal to the area under the PV diagram, which has a rectangular shape. This is the same for the C to D process. Alright, let's update our table for AB and CD works. For the BC process, the line is curved, and finding the area under it is a bit challenging for an algebra-based physics course, so here we already have the equation given. Let's calculate these numbers and fill out the first column of the right table. Next, focus on the change in the thermal energies or the very right column. We have an equation to calculate the change in the thermal energy of an isobaric process. But we don't have a particular equation for an isobaric process, but we know in a complete cycle, the total change in the thermal energy should be 0, so if we find delta E of A, B and C, D, we can calculate delta dA. Let's calculate the numerical values of the change in the thermal energy and update the very last column of the right table. For calculating the exchanged heat, we have all of the pieces. Using the heat equation, we can calculate the numbers. Now we have all of the numerical values we needed for part C. Part D is pretty straightforward now that we have all of the works, heat and thermal energies. To find the net values, we calculate the sum of them. So the conclusion is that, in one cycle, the surrounding environment compresses the gas, and gas releases energy. Thank you very much for watching this video. Please check our website, physacademy.com, or our YouTube channel for more practice problems. If you found it helpful, please consider subscribing to our channel.